Hi, my name's Andy Spoon. In this video we're going to take a look at getting started with Pasco Capstone software. I'm also going to be using the 850 Universal Interface connected to our Passport motion sensor, which hanging above is a spring with a mass that's going to be oscillating. Now, to confirm what I have connected here to my Pasco Capstone software, I'm going to begin by taking a look at my tools palette and opening up the hardware setup. This is found down the left hand side of your screen at the top of the tools. You'll see that I have the 850 connected, showing all the ports available, and you'll see that port number 4 is connected to my motion sensor, which is confirmed by this green line connecting them. I can quickly dismiss the hardware setup just by clicking on it again. Now let's start getting ready for data collection. I'm going to begin by selecting one of the quick start templates. I'm going to choose the table and graph template, and I'm going to go ahead and select my measurements for these columns. So I'm going to put position and velocity in my table, and I'm going to select position for my graph measurement. Now we can begin recording by selecting the record button in the lower left hand corner. Let's go ahead and oscillate our spring. You'll see that we have live data collection going on in our table and our graph, and we can further zoom in on our graph by selecting the scale button in the toolbar. Notice that our graph also is scaling the time axis to make sure that all the data is visible. So let's go ahead and stop recording. And now I'm going to make a full page graph, which will allow me to add a couple plot areas and also allow me to dismiss the table, which I'm not really using right now. So let's insert a new page by clicking on the Add New Page button. And instead of choosing one of the templates for this one, I'm going to double click the graph button in my displays palette. This creates a full screen graph where I can select my measurements, and I'm going to begin with position and add a couple other plot areas for velocity and acceleration. And once again, I can scale all those at the same time. Notice right now I have run number 1 showing. Let's go ahead and see what happens whenever I start recording run number 2. You'll see that the default behavior is to hide run number 1 and only show you one run at a time, which in this case is the most recent run number 2. Let's stop recording, go back into our toolbar, and you'll see the Run Display Options button has a drop down beside it. This shows me all the runs that are currently available, and you'll see run number 2 is checked, but I can quickly select run number 1 to take a look at it. Now let's say we want to look at both of the runs at the same time. The Run Display button also is a toggle for that behavior, so now I can go through and select more than one run. So I see run number 1 and run number 2. And let's go ahead and collect run number 3 to see what happens. And now you see both my 2 previously recorded runs and run number 3. And let's go ahead and stop recording. So just to confirm that this graph is not just showing me my runs, I can also see what all my runs and measurements are available via my data summary, which is the next button found in my tools palette. Here you'll see that I have a motion sensor connected, which has position, velocity, and acceleration data available, and I have 3 runs for each one of those. Now let's pin that to our screen by clicking on the pin in the upper right hand corner of that box and delete the last run. Now notice when we deleted that run, it removed it both from my graph and also from our data summary. You may have also noticed that we didn't get a confirmation dialog asking us if we really were sure that we want to delete that run. And that's because Capstone has the ability to undo all actions, including the deletion of runs. So let's go ahead and hit that undo button. And now you see you have run number 3 reappear in your graph and back inside of your sensor data summary. I can dismiss the data summary just by selecting it again in the tools palette. So for this last step, I want to go through and customize my graph so I can present it to my teacher. So let's go ahead and uncheck run number 1 and run number 2. Just zoom in on run number 3. I'm also going to go ahead and turn off my title, which is shown by default here in the lower left-hand corner. I can do that by selecting my graph display properties. And notice this is also where you will have other further control on your graph display options, such as your active data appearances, your future data appearance, the display background options, the display appearance. Notice that my show title is currently checked. That's a default behavior, so I'm going to go ahead and uncheck that and confirm that with the OK button, and you'll see that the graph title is no longer being shown. In my last step, I'm going to take a look at how to smooth out some of our data. And let's take a further look at what I currently have. So in my position plot area, I have my position data for run number 3. Velocity is the first derivative of that position data, and it looks fairly smooth. Acceleration is my second derivative of that data, and we're starting to see that it doesn't look very smooth at all. Well, Capstone introduces the ability to quickly access the smoothing of that data. So just confirming that you have that plot area selected and that data selected, we can go up into the toolbar and slide it, and you'll see very quickly with just a little bit of the movement of that slider, we're able to slide our data. And this can be done individually for each one of my plot areas, so I can also do this for my velocity. So that's how we can finally customize our displays so we can present them later on. Thanks for joining us in this video. I hope you enjoyed it.
Hi, this is Brett Sackett with Pasco Scientific, and I'm here with
JJ Plank with Pasco Scientific.
So JJ and I were talking about the smart cart, and we got to wondering, how much physics can you do with the smart cart?
Well, Brett, there's a lot of physics we can do with the smart cart. So much physics that we can't talk about all of it today. However, we will show you some of what we think are the best applications, starting with some topics in kinematics.
In one dimension.
That's right.
All right, let's rock some physics with the smart cart.
Acceleration on an incline.
And even free fall. Hey JJ, how about we do some dynamics? Newton's first law.
Newton's second law.
Newton's third law. JJ, has the smart cart done enough physics yet?
Absolutely not.
All right, let's do some work and energy. Work-energy theorem.
Hooke's law. Lots of great work and energy applications.
As a physicist, I love all forms of energy. But you know what I really love about the smart cart? Is that every smart cart is fully customizable.
Some other great applications include topics in momentum,
Elastic collisions.
inelastic collisions,
Explosions with equal masses.
explosions with unequal masses.
You know, JJ, with a built-in force sensor, encoder wheel, accelerometer, and gyro, there's so many things you can do with a smart cart.
Well, let's take a look at some of those additional applications.
Let's do that.
Simple harmonic motion. Centripetal acceleration.
Centripetal force.
So the smart cart obviously makes a great tool in the student lab environment, but it's also a very useful tool for demonstration purposes.
We've taken a look at a lot of the applications for the smart cart. Let's have a quick review. And with Pasco's 5-year warranty, you're sure to never get a lemon. Thanks for watching. This is Brett and JJ with Pasco Scientific. We've shown you a lot of things that you should absolutely do with the smart cart in your classroom. So we're going to leave you with one thing you should definitely not do.
Hello, I'm Elizabeth Kennedy, and we're here today to talk about the Pasco Color Mixer, which is a brand new product, very exciting. I think you're really going to like it. As you can see, the Color Mixer and a white background screen mount on the Pasco optics track on the bench here, but it's not necessary to use the bench. You could use a white wall, you could use your whiteboard, you could stand these pieces just like this. It's helpful to have the bench. I like to use it because it keeps things more stable, but it's not absolutely necessary to have it, which is part of the versatility. The color mixer, as the name implies, joins three colors, up to three colors of light together. And we'll start out and we'll have a look at the first color, which is going to be red today. And I'll use this sturdy little knob on the back to just turn on the red, and I'll dial it up from not on at all, very low intensity, all the way up to high intensity, to its brightest. And there it is. It's a beautiful circle of red light. Now, I can take another color, such as green, and I can ask myself, what would happen if I mixed green light with red light? Well, if I turn it on just very, very low at first and bring up the intensity, I can see that the green light and the red light overlap in this region, and when they do, they create yellow light. Maybe not what I would have predicted, but it turns out that that's the case. Now, I had the red light on and I brought up the green light. Suppose I turn down the red light, and let's see what happens to the yellow color. As it goes back to just green, it fades through a series of more and more green colors, almost a lime green. So now I can turn on the third color of light, and mix it in, the blue. As I bring up the blue light, I see the regions of overlap between green and blue and red and blue, and in the region of overlap of all three of the lights, I see a combination that looks very much like white light. So using just three colors of light, I can create many other colors, in fact, all the colors necessary to have a color television, for example. Now, also, if I would like to, I could use the optional set of cards that include both transparencies and reflective colors. This can be purchased in addition to the color mixer. It's really a set of trading cards, if you want to think of it like that go along with the visible spectrum of light. So the trading cards, the transparencies and the reflective cards, have on them a graph, in this case the percent transmission versus the wavelength, and I can get an idea of what wavelengths of light will be transmitted most intensely through this color of filter. So let's try this. We'll start with red, so I'll turn off the green and the blue light, and I'll take out one of the filters. I think I'll start out with a red filter. And I'm going to cover up the light, the red light, with the red filter. Let's see what happens. Okay, that is the red light covered with the red filter. Next, I'll experiment with the blue light that we saw a minute ago, with the blue transparency here. This blue filter I'll go and put in front of the red light, and it transmits virtually none of the red light that we can see. Okay, so that's an example of the filters, the red and the blue. Now let's see what happens when we reflect light from different colors of cards. First, let's try red light on red light. So I'll put this reflection card with, you can see now it has a graph of relative intensity of reflected light versus wavelength. I'll put this in front of the red light, and it reflects red light. I'll use a green card. I'll put the green card in front of the red light. And now, I think just out of curiosity's sake, I'll put the green card in front of blue light, see what happens. So here is the green card in front of blue light. Okay. Now, we also have, in this optional set of cards, two yellow cards, one of which is just regular yellow paint or pigment, and the other of which is fluorescent yellow. So I'll put the regular yellow card in front, And then I'll follow that with the fluorescent yellow card. So regular yellow versus fluorescent yellow. And there you have it. That is a look at the fantastic, awesome new Pasco color mixer.
The Pasco PS2103A motion sensor is used to measure and record the position, velocity, and acceleration of large and small objects moving in one dimension toward or away from it. The motion sensor makes measurements using ultrasonic pulses emitted from the gold transducer on the front of the sensor. These pulses travel out in one dimension from the front of the sensor until they hit a target object, at which the pulses are reflected back to the sensor. Given the time it takes the pulses to make a round trip, and the speed of sound in air, the sensor can indirectly measure the distance or position between itself and the target object. The sensor then uses subsequent position measurements to determine the target object's velocity, and subsequent velocity measurement to determine its acceleration. Because the sensor uses ultrasound, it's sensitive to obstructions that may block or be near the target object when making measurements. Be sure to clear any of these obstructions from the one-dimensional path of the sensor when making measurements. Also, the sensor has a minimum range of 15 centimeters and a maximum range of 8 meters, and is sensitive to the type of surface from which the pulses are being echoed. A harder surface will generally produce measurements with less noise. When making measurements, the transducer on the front of the motion sensor should be aimed directly at the target object. Use the rotary dial on the side of the sensor to aim the sensor at the target object. On the top of the motion sensor is a selector switch that is used to adjust the range of the sensor when measuring larger objects at longer ranges and smaller objects at shorter ranges. Use the cart setting for smaller, shorter range targets and the person setting for larger, longer range targets. The motion sensor can be used in many different configurations, including placed flat on a lab table to measure the horizontal motion of an object moving toward or away from it, adjusted to measure the vertical motion of an object, mounted to a support rod vertically, or mounted horizontally, or you can use the integrated clips on the front of the motion sensor that allow it to be mounted to the end of any Pasco Dynamics track or Pass track.
Hello, I'm Robert Morrison, and today we're going to take a look at conservation of energy. This lab write-up comes from our Physics Through Inquiry manual. To do this lab, we're going to need a few items. We're going to need a rod stand, we're going to need a pass track, we're going to need a clamp for the pass track, we're going to need a motion sensor, an angle indicator, a pass car, an end stop, and an interface for collecting data. So let's take a look at the physical setup, and then we'll take a look at the data and some of the analysis. I'm going to connect my pass track to my rod stand using the clamp. It fits right in the rail here on the side, slides into place, and then locks down using the nut. I'm going to place that on the rod stand here and give it a pretty good angle and set it into position. At the far end of the track, I'm going to mount the end stop. I'm going to try and get this as close to the end of the track as I can. Again, I'm mounting that into the rail and locking it into place. And then with the cart, I'm going to extend the plunger, and I'm going to set it on the track against the end stop. And we'll see why that is in just a second. I'm going to take my motion sensor, and I'm going to connect it to the end of the track. Fortunately, being a Pasco motion sensor and a Pasco track, it snaps right in. And I'm going to make sure that it's pointing directly at my cart. I want to make sure it's facing the face here. And that I have it in the cart position on the switch. So that's all set. That way I'm not looking at any other thing in the room, the rod stand, the computer, any of that stuff. Then I'm going to connect that to my interface. Okay, that is pretty much the physical setup of the lab. I'm then going to measure the angle of the track. I'm using a Pasco angle indicator. This is really useful when you're doing it with the track. If I wanted to, I could mount it to the track. If I was looking at multiple angles, that lets me measure the angle from the same point each time. But since I'm just going to be looking at this angle once, I'm going to go ahead and set it on the track, take a look at that angle, and record that for later. Okay, I'm pretty much ready to start collecting data. I'm going to collect the first run with the cart in position. I want to do that because I want to look at the initial position of the cart just as it's leaving the end stop here. So I'm going to collect that first run. That ticking indicates that the motion sensor is functioning. So I'm getting that initial distance to the cart. And I'm going to take about 10, 15 seconds of data, and then I'm going to go ahead and stop. So now I have my initial position. Now I'm going to go ahead and take my cart, and I'm going to press the plunger into place, make sure it's locked, and set it once again in front of the end stop. And we're good to go. I like to use an object to launch the cart. This gives us a little crisper launch each time. I'm just using a mounting bracket for the track here. Ruler works really well too. So I'm going to go ahead and start collecting data. And then I'm going to launch the cart. I'm going to let that bounce a couple times because one of the things we're going to discuss is loss of energy as one of the factors that affects the accuracy of the lab. So I'm going to go ahead and hit the stop button. And we're going to go ahead and do some analysis. And that's all there is to the data collection. Okay. On the analysis side, I'm looking at a graph of position versus time. And I'm going to be looking at the value of position from the initial position, that first run, to the first peak in that position versus time graph. So I'm going to extend that a little bit. You also notice that we've been collecting data at 20 samples per second. The default for the sensor is 10 samples a second, so we did adjust that earlier. Now I'm going to be looking at the difference from the initial position to the final position. So let's go ahead and look at the select tool. And I'm going to select above that point and below that point so I can get a range of data, and I can adjust that until I have just the points that I'm interested in. And once I have those points in the selection, I'm going to go ahead and hit OK. And so what I'm looking at is the final and initial position because I want to look at the difference. To do that, I'm going to use one of the tools I have here, the coordinate tool. And I'm going to look at the difference between the initial and the final. So I'm interested in the y difference here, so dy, and that is 0.23 meters. Excellent. And so that's going to be the distance that the cart traveled up the track. That's going to help me calculate that final height so I can find the potential energy, the maximum potential energy of the system. And I'm going to look at a second graph, which is the velocity of the cart on the track. And that was recorded right alongside the position. And I'm going to be looking at the initial velocity. That's the velocity just as the cart was leaving the track. So that's the maximum velocity down here. So I just need the value for that point. So I'm going to once again bring up a palette. I'm going to use the selection tool. I'm going to highlight the point that I'm interested in. And I'm going to say OK. And I'm just going to get the coordinates for that point. So the y value there is the maximum velocity of the cart. Okay, so now that we have what we need to calculate the maximum kinetic energy at the bottom of the track and the maximum potential energy at the top of the arc, and we can compare those two things and find out if energy has indeed been conserved. To calculate the maximum potential energy, we're going to define the difference in height. We're going to use the distance that we found earlier and the angle of the track to calculate the height, and then from the height, we'll calculate the gravitational potential energy. Now we want to compare that to the maximum kinetic energy, which we found at the bottom of the track. We're going to use the velocity we found earlier to make that calculation. We compare the two and find that, in fact, energy was conserved. We hope you find this lab useful, and we'd love to hear your feedback. Thank you.